igneous rocks form from cooled magma or lava, you may wonder, why are there different types of igneous rocks? Why are some igneous rocks dark-colored, like gabbro, and others are light-colored, like granite? In the early 1900s, a Canadian geologist named Norman L. Bowen designed a laboratory experiment where he cooled molten rock, magma, and monitored how the mineral composition of the solidifying igneous rock changed through a range of temperatures. What he observed was a repeatable, predictable sequence of silicate mineral crystallization that we now know as Bowen's reaction series. As he cooled the magma and crystals began to form, Bowen noticed that new minerals formed because the arrangement of atoms in the minerals changed, and so did the elements that made up those minerals. Bowen called this sequence of mineral formation from olivine to biotite the discontinuous branch, because during each step, a new mineral formed. In order to picture what happens when crystals form from a melt, let's zoom in on a pool of magma similar to what Bowen observed in his experiment. Notice that there are a variety of elements and ions within the melt. As temperatures cool and crystals form from the melt, they remove certain elements. The first mineral to form from the melt is olivine. Olivine is a very simple mineral to form. It contains iron, magnesium, and silica ions, which are isolated from each other. In other words, no oxygen atoms are shared between neighboring silica tetrahedra. Because olivine is rich in iron and magnesium, as it crystallizes, the melt becomes depleted in iron and magnesium. As the temperature of the melt continues to decrease, a group of minerals named pyroxenes form. Pyroxenes and olivine contain similar elements, but the atomic arrangement of those elements is slightly different, which is why pyroxene minerals look very different from olivine crystals. The silica ions within pyroxenes link up into single chains, which means that each silica tetrahedron shares 2 oxygen atoms with neighboring tetrahedra. Both pyroxenes and olivine are iron and magnesium-rich silicate minerals, so now that both have formed, the melt has a lot less iron and magnesium in it. That means, as temperatures continue to decrease, the minerals that form can only be made using the elements left over in the melt. Amphibole minerals form next, at cooler temperatures. Amphibole minerals contain sodium, calcium, iron, magnesium, and silica, so as these minerals form, the melt is now becoming depleted in those elements. Amphibole minerals have silica ions linked together in double chains. Finally, with continued cooling, biotite forms from the elements left in the melt. Biotite contains potassium, aluminum, and silica, and can incorporate any leftover iron or magnesium. Biotite is what geologists call a sheet silicate. 3 oxygen atoms within each silica tetrahedron are shared with neighboring tetrahedra to create a sheet. The minerals that form first at the highest temperatures of Bowen's discontinuous branch are iron and magnesium rich, what geologists call mafic minerals. As temperatures decrease, less and less iron and magnesium are available in the melt to make minerals like amphiboles and biotite. Instead, elements like aluminum, sodium, and potassium are available in the melt to make what geologists call intermediate minerals. While mafic and intermediate minerals form in the discontinuous branch, another mineral, plagioclase feldspar, forms as well in what is known as the continuous branch. Similar to the discontinuous branch, as temperatures cool, plagioclase changes its elemental composition in a solid solution series that incorporates more calcium into its crystal structure at high temperatures, making a dark gray version of the mineral, and more sodium at lower temperatures, making a white version of the mineral. However, unlike the discontinuous series, the arrangement of the atoms in plagioclase does not change as temperatures cool. Therefore, because the atomic arrangement remains the same, the mineral is still plagioclase, just with a slightly different composition in what Bowen called the continuous branch of the reaction series. At cooler temperatures, the discontinuous branch and the continuous branch merge, and the minerals that form become more felsic. That means that they have less iron and magnesium in them, and more lighter elements such as aluminum and potassium. The formation of muscovite and potassium feldspar uses up most of the remaining aluminum, sodium, and potassium from the melt. By the time quartz forms, there is almost nothing left in the melt except for silicon and oxygen, which, when combined, form the mineral quartz, silicon dioxide. Felsic minerals, like quartz and potassium feldspar, have all 4 oxygen atoms in each silica tetrahedron, shared with neighboring tetrahedra. Quartz is the final mineral to form in Bowen's reaction series. Because it forms at the lowest temperature and has all of its tetrahedra covalently bonded to neighboring tetrahedra, quartz is extremely stable at Earth's surface temperatures and extremely resistant to weathering. That's why beach sand, which has sometimes traveled hundreds to thousands of kilometers from its source, is most often made up of quartz grains.